So in our project, short-term prediction was defined as a continuous real-time prediction of traffic conditions that occurs somewhere between 15 minutes into the future and 1 hour into the future. There's now a growing body of research evidence and successful real-world deployments to show that these short-term predictions can improve the effectiveness of traffic management strategies and can bring significant mobility and safety benefits. Also, implementing short-term predictions can help transportation agencies realize that the active management cycle illustrated here, where the agency takes an active role in dynamically assessing and fine-tuning the performance of their system. Next slide, please. Slide 4 here illustrates an active management continuum starting at static management and then incrementally increasing towards proactive management. So I believe part of the original motivation for the research project was to, number one, publicize the benefits of proactive management, and number two, to publicize the availability of short-term prediction as a helpful mechanism for moving higher along the continuum shown here. Next slide, please. So an agency's approach to traffic signal timing offers one example of how to incrementally move upwards along the active management continuum. For example, the signal timing approach can evolve from pre-timed to actuated to adaptive and then towards a system that leverages machine learning or microsimulation. But as we will see during the course of this webinar, short-term traffic prediction can enhance many different forms of traffic management, and the traffic signal technology is only one example of the many forms of traffic management that can benefit from STP. Next slide, please. Some of you may be familiar with the pilot ICM deployments in San Diego and Dallas many years ago. I believe another original motivation for the research project was that only a small number of agencies have deployed short-term prediction systems in the years since San Diego and Dallas. So this slide shows an illustration of the innovation curve envisioned by Rogers in the 1960s. So according to this curve, and with respect to short-term prediction deployments in this country, it appears we're only at the early adopters stage. And so therefore, it might be in our best interest to accelerate the adoption of this technology and try to reach the far side of this curve as soon as possible. And there's one more concept that I'd like to highlight on this slide, which is that our research found three primary approaches to short-term prediction. Number one, where the predictions are based on machine learning. Number two, where the predictions are based on traffic simulation. And number three, where the predictions are based on simpler forms of data inspection. And so with that, Mohammed is now going to present the next few slides. Thank you.
Thank you, David. This slide shows the deliverable from the project that David mentioned. We had an information exchange event in Washington, D.C. Last year, attended by about 12 different agencies. And before preceding that, we had interviews with those agencies, the exchange their experience and the type of short-term prediction they have done. We have also produced a primer, about 40-page primer that I'm going to summarize what is in it, and then case studies that David is going to quickly mention and other speakers will talk about. And this is the national webinar that is part of that project. Next slide. In the primer, chapter 1 is introduction. Then we had a chapter that talk about the short-term prediction methods, the experiences with them, and the advantages and disadvantages. In chapter 3, we have a review of how these prediction methods can be used in supporting active traffic management applications and what is the expected benefit based on reviews of previous studies. And then chapter 4, we had a chapter about provide information to support the agency in implementing short-term prediction, how to select the best short-term prediction approach, how to improve the maturity of the agencies in AI in general and in prediction, capabilities, and also how to include that as part of the system engineering process. Next slide. So in general, as David said, that there are two main categories of short-term prediction methods. One of them is data analytics, and one of them is simulation or modeling-based short-term prediction. With regard to data analytics, in the early days, there were a lot of research on using statistical methods like time series and so on. And then more recently, there has been more focus on machine learning methods, both supervised learning like neural network, support vector machine and decision trees and so on, but also unsupervised learning as part of the whole process where you include clustering and so on. There are also other types that could be incorporated, like reinforcement learning, which can be optimized the strategies and so on. And then you have more recent, obviously, these are the three main areas of machine learning, but there are more recent advanced and emerging applications like generative AI and agentic AI and so on. However, that we found, at least in a couple of case studies, that the agency did not use neither statistical or machine learning, but based on data, they come up with an inspection looking at descriptive statistics and visualization and so on to come up with rules about when to activate strategies, implying prediction of when the breakdown or the congestion happen. So that could be a strategy as an initial strategy that can be implemented in the beginning. Next slide. Simulation-based short-term prediction, yes, here. Simulation-based short-term prediction can range from macroscopic and analytical to mesoscopic to microscopic, but also a multi-resolution modeling where you can model different part of the network in different resolutions. You could combine that with dynamic traffic assignment and discrete choice models that predict, for example, shift in managed lane choices and diversions and so on, route diversion and so on. Based on, you could see that simulation can take longer time than machine learning and running in real time. But again, it depends on what are the models that is used and the size of the network. So there is opportunity to model a smaller size of the network than the traditional application of simulation that we saw, for example, in integrated corridor management project, the initial ones in Dallas and San Diego. You could increase the efficiency somehow by looking at your requirement. Next slide. So again, the latency, there is, these are, after you analyze and predict, there is a decision support system that recommended an action, and then you implement that action and you achieve the desired outcome. However, every one of those steps is associated with latency, particularly in the analyze and predict, and particularly if you're going to use simulation. So for each strategy, you're going to have different requirement for latency. So because first of all, you want to implement these in time to implement the right control strategies, because a lot of these strategies require sometimes, for example, in signal control, if you switch from one plan to the next, you need some transition and so on. Also, if you are implementing a strategy that affects traveler behavior, you want that to be activated ahead of time. So you have to have, for each strategy, you have to have a latency limitation or requirement, and then based on that, you decide on the best approach. Next slide. With regard to with this slide, we see that the different the timeline of active management versus or reactive management versus proactive management. With the proactive management, you predict the breakdown or the congestion or the event before they occur, and then you start implementing the action plan, the action faster than what is done with the reactive. That results in ending the congestion sooner than with the reactive approach. But it could be also if you know that something is going to happen or a congestion could happen, you may be able to actually prevent the congestion from happening. For example, ramp metering. If you wait until the congestion happen and then you activate a ramp metering plan, you are already, if we remember the fundamental diagram that we study in the traffic classes, you're going to be in the unstable regime that is going to be very difficult to bring it back to the uncongested regime. But if you know that you're going to be in the congested regime and do a strategy that prevents you from being in the congested regime, then you can activate that, and you may not have congestion at all if you implement the right strategy. Next slide. And this is some of the benefit that we found in the literature. For example, again, if you apply that to predict the incident or the impact of the incident, you could reduce the congestion by 60% according to Yao and Khan. You could predict incident clearance time with 85 to 90% reliability. You can provide advanced warning for a driver approaching incident, and you can reduce fatal and injury crashes by 13%. Obviously, the more of these studies we're going to have and more evaluation of their benefit, that will provide additional information for a future implementation. Next slide. And this slide just shows that how implementing active traffic management can improve reliability. Basically, the width of the band around the average as an indicator of the reliability. And with reactive, it is already doing that, as you see. But with proactive, we expect those bands around the averages, in addition to the averages, will be improved. Next slide. One of the chapters in the primer is talking about how to identify the right short-term prediction methods. Obviously, a machine learning method can be effective when your quantity and quality of data are high and sufficient. And there is no, however, those normally have disadvantages when we want to look at situations where the alternatives have not been implemented in the field. So in that case, you would not be able to know based on machine learning what is the impact of those different alternative plans. With the simulation, again, it requires quality and quantity of data, possibly a little bit less than machine learning, but still have to be high quality and quantity. The geographic limits are relatively small, so that you don't have a big or long time running these models. And it is one of its main strengths is that it allows you to analyze multiple response plan in real time on the fly. You can feed it to the simulation, and you can the results can be fed to a decision support system that can tell us which plan perform better according to identify performance measures. And again, latencies should be considered. The data inspection methods, this could be a good initial way of doing the prediction, and the agencies that has already implemented, some of them said the next step is for them to implement machine learning. And some of the implementation may be simple enough that you don't need to go to a machine learning or deep learning or things like that. So this could be also a method that can be selected from, the agency can select from. Next slide. And this is a project that David and I and other work on for the USDOT JPO program to develop capability maturity model for AI-enabled ITS. Basically, as some of you are very familiar with the TISMO capability maturity model and capability maturity frameworks, this is similar to it, but it's related to AI application. So one can think about it also how it applied to short-term prediction, where on the left you have the institutional dimension like culture and business process and collaboration and workforce. And on the right is the technical part, which is the data and infrastructure, the modeling and application, and the integration and operation. And then cybersecurity is in the middle. It has both the institutional component, the subdimension and aspects, and the technical. That's why you see it's colored as the combination of the two. Next slide. And then we also in chapter 3 or 4 in the primer, we talk about the system engineering process and how the AI and a machine short-term prediction should be incorporated as part of that process, from feasibility study to concept of operation to requirement analysis to design and so on. And then after that to evaluate it and revisit it as time goes by. So that's very important aspect as any ITS application to include it as a system engineering process. I think this is my last slide, David.
Yeah, thanks a lot, Mohammed. All right. So as Mohammed noted a few slides ago, one of the deliverables from the project was a set of 3 fact sheets to publish some of the interesting details about some of the real-world STP deployments across the country. So in the next few slides, I'll describe some of the findings from the real-world deployments at the Delaware DOT and at the city of Dubuque, Iowa. Our third fact sheet was for Cranberry Township in Pennsylvania, but later this hour, we'll hear another presentation from Kelly Maurer that specifically focuses on that deployment. So regarding the Delaware DOT deployment, the research team felt that DelDOT's STP system was a strong role model because it fully leverages machine learning. Other factors that led to DelDOT having a strong system include a statewide strategic plan for transportation management that dates back to 1997, close partnerships with academia and the private sector, the small size of the state of Delaware making it easier to implement certain actions, and finally, a strong support for innovation from agency leadership on down. Next slide, please. This slide highlights some of the technical aspects of DelDOT's STP system. The system has constant access to historic and real-time data from a multitude of sources, as illustrated in the figure. The system can predict key traffic flow metrics between 5 minutes and 60 minutes into the future. The system facilitates real-time changes to the signal timing plans to more seamlessly accommodate disruptions that would have been unexpected by humans until it was too late. And beyond the signal timings, the system can also recommend and implement other traffic management strategies in response to miscellaneous traffic disruptions. Next slide, please. The next example involves the city of Dubuque in the state of Iowa. Similar to the examples from DelDOT and Cranberry Township, the city of Dubuque benefited from multiple decades of previous investments in technology infrastructure. And similar to the Cranberry Township system that you'll hear about shortly, The city of Dubuque also followed the systems engineering process. However, a key difference between this example and the others is that this one leverages traffic simulation-based STP. And notably, the pilot ICM deployments in San Diego and Dallas many years ago also demonstrated the use of traffic simulation-based STP. Next slide, please. This slide highlights some of the technical aspects of the City of Dubuque's STP system. A traffic status change or capacity change, such as an incident, a planned closure, or a demand surge, will trigger a simulation of rerouting alternatives. The simulation model then feeds information to a decision support system. For minor events or incidents, the decision support system can make minor green time adjustments that increase the use of detour routes. But for major events, the simulation model can evaluate different cycle lengths along the predefined detour routes, and the traffic signals along those routes can automatically transition to the cycle lengths producing the lowest delays within those simulation runs. In addition to facilitating the signal timing adjustments, the STP system also facilitates the posting of proactive traveler information onto dynamic message signs within the city. Next slide, please. All right, so thank you very much. This concludes our high-level overview of the outcomes from the project, and so we'll keep an eye on the Q&A pod for questions that you may have. And with that, I believe we can now switch over to our second speaker and our second presentation. Thank you.